So in this video, my intent is to introduce a new type of differential equation known as an exact differential equation. And it often may be presented to you in this form right here: m of xy times dx plus n of xy times dy equals 0. So yes, these are multivariable functions, although realistically in terms of definition, sometimes your m of xy or n of xy could be a single variable function. You can almost look at any single variable function as a multivariable function if you consider logic, like x to the power 0 is 1 or y to the power 0 is 1. But really, it's nothing. All of that is not really too complicated or nothing worth overthinking about. So this is called an exact, or this right here is not necessarily an exact differential equation. An exact differential equation is not made exact by bearing this form. This differential equation is said to be exact if partial m with respect to y equals partial n with respect to x. And if you saw my last video, you should know a thing or two about partial derivatives. I'll actually do them in a more applicational sense in this, with this series on exact differential equations. But when you have a function, for anybody who didn't see my last video, or about 3 videos ago when I explained what a partial derivative is, when you have a function, say f of x, you can take the derivative of that function and you would get f prime of x, or df dx. Just different ways of writing the derivatives in terms, whether you like Lagrangian notation or Leibniz notation. And if you had a function f of x, y, on the other hand, you can't simply take the derivative of that function because it's got more than one input variable, but you can see how the output value grows with respect to the input values. So you can take what is called partial derivatives. So a good example would be if I said partial f with respect to x or partial f with respect to y. Those are partial derivatives. And when you take a partial derivative of a multivariable function, if, say, you're taking the partial f with respect to x, you treat your terms of y constant. So if I said f of x, y equals x squared y, let's say, and I wanted to take partial f with respect to x, that would be equal to y times the derivative with respect to x of x squared, and that would evaluate to 2xy. So there's a pretty general example of a partial derivative. They're not too hard to evaluate, and typically that would be in a 3rd semester calculus course that would be introduced. But for testing purposes in Calc 3, you're never going to be tested solely on that, because that's considered to be very easy partial derivatives. But let's diverge more into the theory behind an exact differential equation. So I've already said it, a differential equation is said to be exact, and I'll actually box in the criteria here in red. If partial m with respect to y equals partial n with respect to x. So here I've got the generic form of an exact differential equation, and this differential equation is exact if and only if partial m with respect to y equals partial n with respect to x. And the reason this is called an exact differential equation is because this is based on what is known as an exact differential. And the word exact differential, it's the same thing as a total differential. Sometimes textbooks tend to use either or, but they mean the same exact thing. So I mentioned earlier how you can't really take the derivative of a function f of xy or any function with more than a single input variable, because there's no such thing as the derivative. there's more than one input variable. There'd be more than one derivative. But let's say I took a function f of x, y, and I redefined it. Instead, I redefined it as f of x and y of x. So I write my variable y as some function of x. And if I wanted to take the derivative of the function now, because this would be a single variable function of x, I could say that I could differentiate implicitly and use the chain rule. I could say that df dx equals partial f with respect to x plus partial f with respect to y dy dx. That's the chain rule right there, plus implicit differentiation. And if I multiply the dx's out, then I get that df equals partial f with respect to x times dx plus partial f with respect to y times dy. And a lot of times your function f of xy, you go up here, it'll be set equal to some constant, and then the differential of a constant is simply 0. So why am I explaining this? I mentioned that this right here, this circle, this in red, this m of xy dx plus n of xy dy equal to 0. This is a exact differential equation if and only if it meets the criteria that I specified. And this is what a total differential is, what I have at the bottom, this partial f with respect to x times dx plus partial f with respect to y times dy. Now, the reason why I introduced this is because this partial f with respect to x, for example, is equal to m of xy. Let me change my color here. I don't know how that happened, but so partial f with respect to x equals m of x y, and partial f with respect to y equals n of x y. So I've rewritten the generic form of an exact differential equation based on definitions that have already been made. And I have that partial f with respect times dx plus partial f with respect to y times dy equals 0. And the next thing to do is to figure out which multivariable function f of xy would satisfy this differential equation. And up until now, we've been using integrating factors or separation of variables in my series, but neither of those will work. Actually, one good tip, when you solve a first order linear differential equation, after using the integrating factor, you turn it into an exact differential equation. The only difference is that with the first order linear differential equation, and if you saw the proof that I did, that very generic video, you already know what function it's a total differential of, and you simply have to integrate, because the integrating factor, well, it's always going to be the integrating factor times your dependent variable. That's always going to be what the total differential is, but this time it's unknown what the total differential is. So we'll have to figure that out ourselves. So first things first, I got these two partial derivatives, and they're being multiplied by single variable differentials, and it's all set equal to 0. Under normal circumstances, I really can't just integrate everything or integrate both sides. So what I'm going to do, I'm going to choose one of these. I'll take my partial f with respect to x dx, and I'll integrate that. So partial f with respect to x dx, integrating that, it gives me, I'll call this capital F of x y plus my constant of integration here is going to be a single variable function of y. And this is actually pretty important to sum up. The reason why this is because when partial derivatives are taken, other any terms that are not in the variable that's being differentiated with respect to anything that's considered a constant would be turned to 0. So even by taking the integral of partial f with respect to x times dx, I only partially recover my total function f of xy. So with that being said, now f of x, y, it's equal to this. It's equal to this f of x, y, this capital F, plus c of y. And so the question here is, how do I solve for this c of y? Well, for one thing, we have that the partial f with respect to y of this function is right here at the top. It's being multiplied by dy. So what I'm going to do is I'm going to differentiate my function f of xy with respect to y. So partial f with respect to y equals partial f, capital F, with respect to y plus c prime of y. And the reason why I'm actually putting it like this, c prime of y, is because since it's a single variable function, the partial derivative of a single variable function, or simply the derivative of a single variable function, they're going to be the same exact thing. So after a little bit of algebraic manipulation, I can get that c prime of y equals partial f with respect to y minus partial capital F with respect to y. And so upon integrating both sides, I get that c of y equals the integral of partial f with respect to y, which I'm going to actually write as n of x, n of xy, minus the partial derivative with respect to y of, well, minus our partial big F with respect to y, which was this right here. So the integral of m of xy with respect to x. This is what our unknown constant of y is equal to. Let me consolidate a little bit of parenthesis. All of this is integrated with respect to y. So right here I have the means of how a exact differential equation is solved in a nutshell. So I have that f of xy equals all of this that I've got, that I'm right now boxing in red. And that's in the way that I just demonstrated it to you, where first we took the partial derivative with respect to x, and you could have also done all of that in terms of y. So I'm going to box this in. I'm going to box this in yellow. All of this boxed in yellow right here. This could have also been the way that an exact differential equation could have been solved. You could have started off taking the partial derivative of f, partial f with respect to y. Or you could have started off integrating n of xy with respect to y, and then gone from there and done the same thing. Nonetheless, the process and the answer, the final result would be the same in both processes. Now, there is some discrepancy in which of these two methods you should use when solving an exact differential equation. My advice would be to first integrate the more complicated of the two functions. And a lot of times, if you integrate the more complicated of the two functions, and then you take the partial with respect to the other variable of that result, a lot of times it'll be equal to the other partial derivative that you have in your exact differential equation, and that makes it really easy, because then the unknown the single variable function that was the unknown constant after integration is 0. And when it's like that, you could literally just take either m of xy dx or n of xy dy You could just take one of those and integrate it with respect to the variable that its differential pertains to, and you would get the answer. And one last thing that I absolutely need to add, and somehow I almost nearly forgot, but the solution to an exact differential equation will always be in the form f of x, y equal to some constant c. This will always be the final answer for an exact differential equation. So when you integrate any of this stuff, you don't need to worry about your constants of integration. Just keep it all on the right hand side of the equal sign, and you'll be good.